Plus 1 Chemistry, Chapter 1, Some Basic Concept of Chemistry. Chemistry is the study of matter and its law of combination and change. Classification of matter. Matter, anything that has mass and occupies space, is called matter. Matter can be divided into two, pure substance and mixtures. Pure substance contain only one type of particles. Mixtures contain more than one type of particles. Pure substances divided into elements and compounds. Elements contain only one type of particles. Example, sodium. Compounds contain more than one type of atoms. Example, glucose, C6H12O6. Mixtures are divided into homogeneous mixtures and heterogeneous mixtures. Mixtures having uniform composition throughout is called homogeneous mixture. Example, air. Mixtures having different compositions at different parts is called heterogeneous mixture. Example, soil. Measurement of matter. All substances contain matter which can exist in three states: solid, liquid, or gas. When the properties of a substance are studied, measurement is essential. The measurement system accepted internationally is SI units, International System of Units. Physical quantity in symbol and SI unit in symbol. Length L, SI unit, meter, M. Mass M, SI unit, kilogram, kg. Time T, SI unit, second, S. Electric current I, SI unit, ampere, capital A. Temperature T, SI unit, Kelvin, capital K. Amount of substance N, SI unit, mole. Symbol MOL, mole. Luminous intensity SI unit, candela, CD. Uncertainty in measurement. Measurements involve recording of data which are always associated with a certain amount of uncertainty. The measurements of quantities in chemistry are spread over a wide range of 10 raised to minus 31 to 10 raised to plus 23. Hence, a convenient system of expressing the numbers in scientific notation is used. The uncertainty is taken care of by specifying the numbers of significant figures, means meaningful digits which are known with certainty, in which the observations are reported. The certainty is indicated by writing the certain digits and the last uncertain digit. Rules for determining the number of significant figures. 1. All non-zero digits are significant. Example, in 285 cm, there are 3 significant figures, and in 0.25 milliliter, there are 2 significant figures. 2. Zeros preceding the first non-zero digit are not significant. Example, in 0.03, there is only 1 significant figure, and 0.0052 has 2 significant figures. 3. Zeros between two non-zero digits are significant. Example, in 2.005, there are 4 significant figures. 4. Zeros at the end or right of a number are significant if they are on the right side of the decimal point, otherwise they are not significant. Example, in 0.200 gram, there are 3 significant figures. 5. Counting numbers have an infinite number of significant figures. Example, 2 balls or 20x can be represented by writing infinite numbers of zeros after placing a decimal. That is, 2 equal 2.000 or 20 equal 20.0000. The dimensional analysis helps to express the measured quantities in different system of units. Hence, it is possible to interconvert the results from one system of units to another. Example, There are three common scales to measure temperature: C. Degree Celsius, F. Degree Fahrenheit, and K. Kelvin. Degree Celsius and degree Fahrenheit are related as F equal 9 by 5 C plus 32. Degree Celsius and Kelvin are related as K equal C plus 273.15. Laws of chemical combinations. The combination of different atoms is governed by 5 basic laws. 1. Law of conservation of mass by Anthony Lavoisier in 1789. It states that matter can neither be created nor be destroyed, or in a chemical reaction the total mass of reactant is equal to the total mass of products. Second law, law of definite proportion by Joseph Proust at 1799. It states that a given compound always contains exactly the same proportion of elements by weight. Third law, law of multiple proportion by John Dalton at 1803. This law states that if two elements can combine to form more than one compound, the different masses of one of the elements that combine with a fixed mass of the other element are in a simple whole number ratio. Fourth law, law of gaseous volumes by Gay-Lussac at 1808. It states that when gases combine to form gaseous products, their volumes are in simple whole number ratio at constant temperature and pressure. Fifth law, Avogadro's law by Amedeo Avogadro at 1811. It states that equal volume of all gases at the same temperature and pressure should contain equal number of molecules. All these laws led to the Dalton's atomic theory, which states that atoms are building blocks of matter. Atomic and molecular masses. Atomic mass. Atomic mass of an element is a number that expresses how many times the mass of an atom of the element is greater than 1 by 12th mass of a C12 atom. Atomic mass equal mass of an atom of the element divided by 1 by 12th into mass of C12 atom. Usually, the atomic mass used for an element is the average atomic mass obtained by taking into account the natural abundance of different isotopes of that element. Molecular mass. The molecular mass of a molecule is obtained by taking sum of the atomic mass of different atoms present in a molecule. Mole concept and molar masses. The number of atoms, molecules, or any other particles present in a given system are expressed in the terms of Avogadro constant 6.022 into 10 raised to 23. This is known as 1 mole of respective particles. The mass of 1 mole of a substance in a gram is called molar mass. Percentage composition. Percentage composition mass percentage of an element equal mass of that element in that compound divided by molar mass of the compound into 100. It is helpful in checking the purity of a given sample. Also, by knowing the percentage composition, we can calculate the empirical and molecular formula of a compound. An empirical formula represents the simplest whole number ratio of various atoms present in a compound. The molecular formula shows the exact number of different types of atoms present in a molecule of a compound. Example, the empirical formula of glucose is CH2O, but its molecular formula is C6H12O6. Relationship between the two formulas. Molecular formula is equal to empirical formula into N, where N equal 1, 2, 3, etc. N be calculated as N equal molecular mass divided by empirical formula mass. Stoichiometry and stoichiometric calculations. The quantitative study of the reactants required or the product formed is called stoichiometry. Using stoichiometric calculations, the amount of one or more reactants required to produce a particular amount of product can be determined and vice versa. The coefficients indicate the molar ratios and the respective number of particles taking part in a particular reaction. The reagent which limits a reaction or the reagent which is completely consumed in a chemical reaction is called limiting reagent. The amount of substance present in a given volume of a solution expressed in number of ways, example mass percent, mole fraction, molarity and molality. 1. Mass percent. It is the number of parts solute present in 100 parts by mass of solutions. Mass percentage of a component equal mass of solute by mass of solution into 100. 2. Mole fraction. It is the fraction of a particular component in the solution expressed in terms of moles. Mole fraction equal number of moles of component divided by total number of moles of all the component. Example, if a substance A dissolves in substance B and their number of moles are Na and Nb respectively, then the mole fractions of A and B are given as mass fraction of A equal number of moles of A by number of moles of solution equal Na divided by Na plus Nb. Mole fraction of B equal number of moles of B divided by number of moles of solution equal Nb divided by Na plus Nb. 3. Molarity. It is defined as the number of moles of solute dissolved per liter of solution. Molarity M equal number of moles of solute N divided by volume of solution in liter V. 4. Molality. It is defined as the number of moles of solute present per kilogram kg of the solvent. Molality M equal moles of solute N divided by mass of solvent in kilogram. Some important formulas. Relationship between molarity and mass percentage. Molarity equal mass percentage into density into 10 divided by molar mass solute. Relationship between molality and molarity. Molality equal 1000 into molarity divided by 1000 into density minus molarity into M solute. Relationship between molality and mole fraction of solute Xb. Xb equal M into capital M solvent divided by 1000 plus M into M solvent. Also M equal 1000 Xb divided by Xa into M solvent, where Xa equal mole fraction of solvent. Relationship between molarity and mole fraction of solute Xb. Xb equal molarity into M solvent divided by molarity M solvent minus M solute plus 1000 into density. Also M equal 1000 into D into Xb divided by Xa into Ma plus Xb into Mb. Thanks for watching this video.